Good morning. I'm Claudia Vacano, Executive Director of the D Lab and Digital Humanities at Berkeley. And I'm really excited to be here today to talk about hate speech. As many of you know, hate speech is currently a huge problem that is actually spreading, and it's growing. And it particularly affects marginalized communities, specifically women, people of color, because of the racialized nature of hate speech, and because it really has this way of impacting particularly vulnerable populations. So the first thing I wanted to do is acknowledge the full team here. We forged a partnership with the Anti-Defamation League, and so this actually is part of a 3-year contract that we have with the Anti-Defamation League. And so Britton Heller, the director of the Technology and Society Center at the ADL, is a close partner of ours and has really helped us forge industry partnerships with different folks in the Silicon Valley. And so really this tool is going to help us in moving forward in detecting hate and hostile environments online. In addition to that, we have Laura Jackley, who's a political scientist, and she really led this project through project management and envisioning the entire project and helping us with the report that we wrote. Chris Kennedy from Biostats was one of the 4 team members in the machine learning component, along with Jeff Bacon, who is from linguistics and an expert in natural language processing. Nora Broge is here with us as well for the qualitative methods aspect of the project. She's a sociologist. And finally, Chris Hensch from German was also part of the team. So I'm going to hand it over to Nora, and she's going to quickly go through a couple of our qualitative aspects of the project.
Thanks, Claudia. Okay, so before we could turn over a lovely data set to the machine learning component of this, we first had to work with a team to create said data set based on some literature, some pre-existing studies that had existed, some formal academic definitions of hate speech, as well as lots and lots of intensive discussions with our team members. We decided to, using our data source, compile a team of undergraduate, mostly coders, qualitative coders, to work with us. This kind of gives you a quick sense of the sample data that we were using. We scraped roughly 80,000 comments from our source across these period of times. We selected, based on some of these phrases, as you can see. And then what we did was we took this team of 9 racially, ethnically, and gender, sexual orientation, and nationality diverse team, and we walked them through a bi-weekly process across the summer of a qualitative coding protocol. What we basically did was we started with hate themes generally as a multi-category concept, and eventually after trainings and several rounds of inter-rater reliability to make sure that all of our coders were on the same page, we realized that actually thinking about hate as a binary concept, hate or non-hate, rather than degrees of hate, was a much more efficient way to get through this, in particular because we were dealing with actual human beings, and so there's lots of subjective things that become a part of that, including the fact that not all of our team members were American citizens, and so we're not necessarily familiar with idioms, common colloquialisms, kind of the meme speech and the world of hate speech in the United States in particular. The rest of the team also included among them the American students, had varying degrees of knowledge, expertise, and experience in some of these realms. So after a 3-round series of inter-relator and inter-coder reliability tests, we actually settled on coding for the binary theme of hate, non-hate, and also trying to figure out among the comments that we were coding if the targets of the hate could be identified explicitly or if it was ambiguous or implicit. And from there, the codebook we created, which then allowed us to create the data set, we then turned that over to the machines to actually see what the instance and prevalence of hate was in this world, this corpus that we were examining. And now I'm going to turn it over to Jeff to get much more technical and specific.
Cool. Thanks, Nora. Good day, everyone. My name's Jeff. Sorry, Nora. I won't get too specific, but I did want to talk a little bit about the natural language processing approach that we did take. And so the output of the result of the process that Nora was just talking about, the qualitative coding, was a bunch of comments on various threads, and then a binary coding as to whether that indicated hate speech or not, as given these definitions that have been worked out during the coding process. And so the prediction task in particular was, given this comment, is this hate speech or not? And we took three broad sort of approaches, so I'll talk about them in turn. The first one, loosely, we can describe as classical models with traditional features, and I'll talk about what that means. The second approach was termed as classical models with word embeddings as features. And the third approach is using deep learning methods, which I'll hand over to Chris to talk about in particular. So the first approach the first two approaches of classical models with traditional or word embedding features really serve as baseline for the deep learning approaches and the further approaches that we're going to be developing from here. So we used a large number of features, sort of like standard NLP features of like unigrams, n-grams, surface features in the spelling and like hashtags, things like that, as one set of features, along with a large set of, so here's a description of those features, and this was simultaneously being done freeform in both R and Python by Chris and I to see what we could do. And here's not a complete selection, but the most important selection of what I'm going to term as like traditional, classical models of machine learning. So I'm using that term just as like non-deep learning approaches. And then into that we put the traditional features. And then the second approach was to not use traditional features, but to use word embeddings, so features derived from models like Word2Vec or GloVe or various instances of that, pre-trained on like Twitter data and large text corpora derived from the internet. Given these classical models, these non-deep learning models, we can kind of, at a high level, think about them as boxes with a bunch of knobs to tweak on the sides, and it's important to tweak those in the right way. And so we use two different ways of tweaking those knobs to get the best prediction that we could. One was this teapot approach. It's a Python library that uses evolutionary hyperparameter optimization, sort of like inspired by Darwinian natural selection of like trying a bunch of models and then crossbreeding a bunch of them to go to the next level and adding in some random mutation in order to tweak those knobs in the right way. And the second approach was auto-sklearn, which uses some Bayesian optimization techniques to tweak those knobs in the right way. And so I'll let Chris talk about the deep learning afterwards, which perhaps actually maybe now would be a good time.
Sure.
Thank you.
Thanks, Jeff. Yeah, so we tried a bunch of standard machine learning algorithms, but given the hype of deep learning, we wanted to see how that did and see if we could exceed the performance of those algorithms. So for text analysis, recurrent neural networks are the standard, particularly LSTM. This is a quick chart of a bidirectional LSTM that reads a text both forward as well as in reverse simultaneously. And that can allow it to detect words at the end of a sentence or of a comment that actually influence how it interprets earlier words. So we use the Keras deep learning framework, and it has a bunch of really handy examples if you haven't done deep learning before. We use the IMDb sentiment analysis neural architecture that has a bunch of settings that just come prepackaged for you with sample code in both Python and R, so it's a great way to get into deep learning. And we made a couple key modifications to those defaults. We wanted to have a larger number of words incorporated into the neural network, so these comments tended to be longer than the IMDb reviews. It's also really important to consider early stopping with deep learning as well as models like XGBoost. And that essentially configures the algorithm to double check on the test data if it's starting to overfit on the training data. So if it only looks at the training data performance, a neural network will tend to continue iterating and optimizing its weights, and it will gradually start to pick up noise, and its performance will decline. So the early stopping approach lets it detect when that happens and stop updating its weights and be done earlier. So it can save you a little bit of time as well. Next, we wanted to do cross-validation rather than using a single test data set, because you can get a high variance in your performance estimate if you use only a single test set. So if you have the time and the computation, we'd really recommend using cross-validation, especially stratified cross-validation if you have a rare outcome. In our case, hate speech was only 5% of the observations. We wanted to make sure from the stratified approach that they were evenly distributed across validation folds. And then last change was that we allowed up to 60 epochs or rounds of deep neural net optimization. That allows it to more slowly converge to the optimum setting. So here's a quick example of what early stopping looks like. Just looking at the top chart, the blue dots are the training set performance, and you see it's declining over the course of the training, and the orange line is how it's doing on the early stopping set. So you see it starts to plateau even though the training set performance continues to decline, and so it ends up stopping at about around 37 or 38 rather than going all the way. We didn't know a lot about deep learning, so we said we want to tune these different knobs or hyperparameters, as Jeff was talking about, drop out how many hidden units to use, how complex the word embedding was. But if we looked at all the combinations, we're talking about 20,000 different neural nets that were going to fit with 10-fold cross-validation. It's going to be computationally infeasible. So instead, we used a random search approach that says, let's just randomly sample potential hyperparameter settings. We're not going to test them all, but if we can get a good variety of random points in this hyperparameter space, we should be able to identify some of the better options or combinations of hyperparameters. This is what the kind of results for this look like. If we just look at this final column on the right, we look at the test AUC, and we're trying to get that as high as possible, ideally to the 0.78 or 0.85 AUC we saw for our other models. So deep learning, even when we tried hundreds of different combinations, was only able to get to 0.71 AUC with the best combinations. By contrast, looking at the ROC curve for the standard algorithms like random forest and XGBoost, we're able to get 0.78, actually slightly higher than that. And if we look at the performance across the different algorithms, we see our ensemble method called superlearner did about as well as the Bayesian additive regression tree, which is a Bayesian random forest essentially. And XGBoost was right behind those. Then when we threw away all of our bigrams and our part of speech tags and all the standard features, we said, let's just use our glove word embeddings that project each word to a latent variable space that captures the language meaning of these different words. Got a huge jump in our AUC performance. We got it to 0.85. And BART, again, at the bottom, did really well along with XGBoost, and superlearner just squeezed by for the lead. So just to summarize the different algorithms with standard features and classical models, we did pretty well. Switching to word embeddings was a huge improvement. Those have only been around for a couple years at this point. And deep learning, we weren't able to really exceed the performance of standard methods, which we think is a good reason to always, don't just go only with deep learning. Try some normal methods and try word embeddings without deep learning. Last comment, I think, is that the main feature we were missing from this approach was that we didn't apply pre-trained word embeddings to our deep learning approach. And given our small sample size, if we could have used pre-trained word embeddings rather than word embeddings trained on our sample itself, we might have gotten up hopefully to 0.85 or maybe even above that using deep learning. And we're starting phase 2 of this project and starting from scratch, so we'd love any feedback or thoughts on new approaches or new things to consider. Thanks. Oh.
I just wanted to mention that our next phase, we're going to be partnering directly with different platforms. So we're actually working with different industry folks to look at the amount of hate speech that they have on their platform and actually work with them to give them an index of that. And then at the next phase after that is a tool that's going to be a standalone tool that anyone could use. So we're looking forward to all of those different phases.